I don't get why it doesn't announce here. That's recording to the cloud though. It's probably my my audio isn't turned on, right? My speakers aren't turned on. Is that down here or something?
Okay, no, you had a speaker. It's off.
Which one? Oh, this thing.
Yeah.
Okay.
Yeah.
All right. Okay. Now they can hear you.
I can hear
That's
you,
good.
Professor.
That's good. Thanks. Yeah. All right. Good. We resolved that. What time is it anyway? Where are we now? We're at time. All right. So that's good. All right. Nice. Thanks. Okay. I just have to figure out what I'm doing. All right. We need to do, I need to go through two things for this paper. That's what. So one is slide 89-2C, which I didn't do yet. So these are two key elements. Slide 89. Okay, so last time I went through this Debye equation, which is will give you the curve for a Polymer coil. Like in other words, at high Q it gives you power -2 because high Q exponential. You got to turn it off. Mute it, yeah, because it's like echoing there. Anyway, this thing goes to 0 at high Q. Like when you get a large negative power, there's a 0. At high Q, this thing's larger than 1, so just have Q. Q cancels with Q squared, and Q is Q squared Rg squared. So that's 2 over Q squared Rg squared. So at high Q, you get this function. And that's the accurate one for Polymer coil Gaussian chain. That's the exact answer that Debye got in like 1948 or something, I guess, like during the war. Something. Right. But and then at low Q, so if you do low Q on this thing, then you can expand the exponential. That's going to be 1 minus Q plus Q squared over 2 factorial plus Q cubed over 3 factorial, which is 6. Right. So the first two terms cancel out at low Q. Then you have Q squared over Q squared gives you 1. So it's Q squared over 2, and you have a 2. So that just gives you 1. That gives you 1. The next term is Q cubed over 3 factorial. So Q cubed over 6, but it's a 2. So it's Q cubed over 3 divided by Q squared is Q over 3. So you get, and Q is Q squared or G squared over 3. Then if Q is small, you can turn that into an exponential Guinet's law. Right. So both things work, and these are exact. Right. So this function, Ornstein, Zernike, and Zernike won the Nobel Prize for the microscope, the confocal microscope, right? But he also did this thing about correlations and stuff. Anyway, in a footnote to one of his papers, he says, "Oh, this function could describe random systems," but he says it's not an analytic function. It's just a fitting function. Like it doesn't have any meaning, right? Okay, so anyway, people kind of gravitated onto this function. And it looks a lot like this function because at high Q, it's Q squared, so Q to the minus 2. And at low Q, 1 plus Q squared, that thing gives you exponential of this thing, right? And then it's 1 over, so it's negative X. So it looks like Guinet's law, kind of. It's kind of similar to that. So if you said that, then you'd find out that this correlation length that Ornstein talked about, but this function is bogus, it's just like made up. That ends up giving you that's 3 times that gives you Rg squared. If you compare this and that, you find out 2 times that is Rg squared. So this is the actual calculated thing for polymers. This is a bogus fitting function. You can see they aren't the same. Like they don't give the same answer. The main point is that this number has no meaning. Like that correlation length that you get out of this isn't meaningful. Right. So that's the thing. So this paper uses this function. That's why I mentioned that. Then that's one thing. This slide 92. Not in this, slide 2C 92. The other thing is and then there's a whole family of these functions, because the Fourier transform of that gives you this, which isn't symmetric. So correlation function has to be symmetric about 0, and this isn't. So basically, this is a bogus function, and that's been like expanded on to make a bunch of scattering functions that are equally bogus, right? So you start with this thing, and you Fourier transform, get that, and then you get this other family of functions that end up being these other bogus kind of scattering functions. So this is 92. It used to be 92. So anyway, this is the other point. So that function's 0.1. 0.2 is 3 points for this paper. So it's a lot, but basically, so if you take something like a fleece, right, and then like you look at it from far away and it's just a solid thing, right? It's a solid object. But if you zoom in, then you can see the fibers. Okay, so scattering is kind of like that. If you shoot a beam at it, at large scale, it just sees like the density, the overall density doesn't see any structure until you zoom in to high Q. So Q is 1 over size. So at high Q, you see the fibers. And the fibers are the same as if you had a fiber alone, or if you put a fiber into this thing. It's the same fiber, right? So that means that as you increase the, so if you have a less and less dense fleece, you see more and more of the fiber, the larger sizes. And if it's a denser fleece, so if you have a higher concentration of fibers, then you see smaller and smaller size. So this is kind of what happens in scattering. So if you just have the polymer chains and the solutions, you have contrast like that, you can see 1, you can see power 2, power 5/3 for good solvent, then 4. And then as you increase the concentration, you can't see the chain anymore. So that thing is gone, and then you get this correlation length shows up. And then that thing diminishes the higher the concentration. The rate of that diminishing is how well the fibers mix. So they can mix well or not well. If they mix not well, it drops slower. If they mix well, then it drops faster. Okay, so that's kind of the idea. So to deal with that, there's a lot of, so it's like you have one sheep, you can't see the sheep anymore once it's in a flock. This guy's supposed to walk. He walks, but I think you have to click him or something to make him walk. There. Anyway, this guy Karsten Volt made this. Anyway, so that you see, if you put in polymers a different concentration and you normalize so the intensity would go up with concentration. So you divide by concentration, then it just drops as the concentration increases because of this screening effect. The same way, so if you change the temperature, so this is at 1 concentration, if you change the temperature, it also will drop. So if the temperature goes up, then the chi gets more negative. So this thing drops more at higher temperature, and lower temperature it goes back. So it kind of goes, so there's a function, this RPA equation describes this thing. So chi negative means it mixes. That means this is positive. So 1 over the intensity gets larger, so the intensity gets smaller. So the more negative chi is, so the better the miscibility, then you get a bigger depression of this thing. So the amount of depression of this thing is a measure of the miscibility. It's a measure of the enthalpy of the interaction. So you can measure this, you can measure the chi. Right. So that's what they do in this paper. They measure the chi by looking at how this drops. Right. So in this is the RPA equation. So the 0 is the dilute one, the top one, and then that's diminished. So if you go to high concentration, then this term dominates. Okay, if you go to high Q, okay, then the I is small. 1 over small is big. So at high Q, the dilute one dominates because intensity is small. 1 over small is big. Then that overpowers this thing. Then you get the normal one at high Q. And at low Q, intensity is high, and this is a log scale, so it's really high. 1 over a really high number is a really small number, and then this thing dominates. So this thing makes it diminish as you go to high Q, low Q. That's how that function works, right? There's a theory behind it, but basically that's kind of how the thing works. It's an inverse. So you're looking at inverse of the intensity to get the enthalpy. And this is related to the osmotic pressure. We don't need to talk about that. This is the function they're using to get the chi parameter in this paper, this RPA equation. So you can say, like we said before, well, you're going to see this is the curve. So if you have a concentration blob, when they overlap, they're Gaussian because they're in a melt. And then at some point you zoom in and they're isolated, so they're expanded coil. So if you go out in Q to smaller size, see Gaussian, and then, so how did you get that curve? Because the curve you're seeing here is this bottom curve. It's described by the RPA to get chi. This other curve won't give you chi. So that top curve is done this way. So you take your polymer, and then in neutron scattering, hydrogen and deuterium have opposite index of refraction. So if you mix things with deuterium and hydrogen, you can actually get 0 contrast, or you can get any contrast you want by those two. They're the largest and smallest numbers in the periodic table. So because it's got to do with nuclear spin, not to do with anything like electron density. So you can deuterate a chain, or you can hydrogenate a chain. So you can have your solvent deuterated, hydrogenated. You can mix those two and find where it perfectly matches your polymer, and your polymer disappears then. So you have this mesh of disappeared polymer that's hydrogenous, and hydrogenous is cheap and deuterated is expensive. In other words, $10,000 per gram. So it's a lot, it's more than cocaine, you know. So I mean, so basically the red thing is cocaine, the other stuff is just goo. Right? So basically you're going to put in 1% of cocaine and a lot of sugar. Yeah. So anyway, so there's that thing's going to light up like a light bulb, and then you can get this curve from that if you put in a dilute of your wine. And also, if you want to see what's the structure of a chain in a melt, as you do the same thing, you put in 1% of deuterated, and then you can see how the chain changes in a melt. Right. So that's a trick people use. So you can get that top curve, but generally the easiest thing is to get this curve and get this, and you get more information from that curve because you get this interaction parameter, and you still get this screening length, and you kind of know what this RG is. You can kind of calculate it. Right. So that's a picture that you need to know. There's one other thing that I need. Slide 3, the 3 slides. Let's see. The 3 slides. Oops, I'll do that. Oh, the 3 slides. They're here. 2C3, that one. Yeah, okay. Now I want number 13 of this. This is just a reminder. We did go through this. Okay, so we did all this stuff. We said that we had that this concentration blob size is going to be related to C by C star to some power. You just assume that everything's to a power in polymers. And then R is out front. And R is going to be a good solvent, so it's 3/5, 5/3 to DF and 1/ds 3/5. And C star goes with the 4/5 power for a good solvent. So it's 4 times P for the C star, and then the R gives you the 3. And then this thing can't depend on the molecular weight because you screened out the molecular weight. So you can't tell me like how long is a fiber in this coat. You can't tell me because you can't see one fiber, right? So that thing can't depend on. So this thing has to equal 0. That means that power has to be minus 3/4, right? So we went through that. Yes, that's kind of one of the main conclusions. This guy, let's see if I can find this thing now here. So we got this paper, which I haven't opened yet. Just 2 things to open. This guy can hide. This guy can hide somehow. All right. So with that, O'Connell, and then the O'Connell's supplemental, and then I sent out that Igor, so you can either open this. This is an Igor, what they call Igor experiment, the PXP. So you can open that. You can use that. I wanted to go through how to use that program at some point, but basically that thing is digitized. That's the Igor experiment. That's not what I wanted. All right. I thought I made it. Oh, I didn't link the file. That's unfortunate. I can put it up on my thing anyway. So I didn't link. If the file's up there, but it's not linked. Anyway, so this is a paper. So anyway, so first off, let me just zip to the end of this where he shows the 3/4 thing, since we just said that, right? So here he's got the 3/4. He's got his, so remember the this thing 3, slides 3. So this thing ends up being the correlation length, or the blob size divided by R would go to the 3/4 power, right? So that's what he shows here. The blob size divided by R versus C gives the 3/4 power. So that's kind of good. So he shows that. That's pretty good. All right. So what's this guy doing? So this is the problem. So this is stuff. All right. This polymer. Okay. So if you put hydrogens on these 2 things, That's called polyphenylene oxide. So it's a polyether, like polyethylene oxide would be 2 carbons here, and polypropylene oxide would be 3 carbons. If you put an aromatic ring, that's polyphenylene oxide, and that's miscible with polystyrene. Polystyrene, the problem with it is it cracks. Like if you have a clear, like a Scotch tape container, it's usually polystyrene, and if you bend it, it cracks, right? So it crazes, they call it. So it makes small flaws and they propagate, make a crack, and it's just as easy to crack. So there's 2 ways to get around that. You can take butadiene rubber and mix it in and polymerize the butadiene while you're mixing it, and you can make a high impact polystyrene, which is cloudy, but it's tougher, like it won't crack as easily. Sometimes if you have a beer cup or something, like this is polystyrene, right? So they make beer cups, some will be like whitish, translucent. So the ones that aren't translucent, if you bend them, they just crack. And the ones that are that's high impact polystyrene. The other option, so this is all developed by General Electric, which is now Sabic. So the Saudis bought the largest polymer company in the US, basically. I mean, so there are 2, like DuPont developed all the condensation polymers like polyester and Kapton, and then GE did all the vinyl polymers, I guess polystyrene, right? And Dow did some polystyrene too, but GE invented, like GE was like the 2 companies, DuPont and Dow, were like the heart of the entire polymer development in the 60s, 70s. All the geniuses were there, so anyway, eventually GE went through all these Jack Welch stuff, where they sold off everything and fired all the scientists and things. Then finally, one of their key components was this polymer thing. It was like their star of the company, they just sell it to the Saudis, So Sabic is now that. When Sabic bought it, they paid too much. So they fired half the staff and they made everyone work twice as hard, So it's kind of like a funny thing. Anyway, I guess it's an okay company to work for now. They're in Indiana, they're not far from here. Like they're like actually the Indiana-Illinois border, they're out that way for Evansville, Indiana, which is like on Route 70, so it's not far from here. Anyway, they use this PPO, polyphenylene oxide, mixed with polystyrene. That makes it really tough, almost like polycarbonate. It's called Norel, but this stuff is a little bit more expensive than polystyrene, so the price is higher. So it's kind of a competition between Norel and polycarbonate, for kind of tough, clear polymer. Anyway, so this thing PPPO. So PPO, polyphenylene oxide. This thing has a weird feature that it'll absorb any solvents, including ethanol, alcohol, like a mad. And if you heat it up, it releases it. So it's like a magic alcohol absorption sponge. Which, I mean, one of the uses of this polymer is just you can make a powder of it and stuff it into a tube. And then if you've been drinking, you can breathe into it and it'll suck all the alcohol out. If you take that tube and heat it up, you can find out if you're drunk or not. So that's a breathalyzer test, right? So this is the breathalyzer test polymer. Breathe into the tube, So anyway, anyway, then if you in that process, you want to have like small particles so that they have a lot of surface area and they can suck up a lot of alcohol, right? Or what it can also use it, I think, like chemical weapon cleanup or whatever. It'll absorb anything, right? So any kind of organic molecule, it just sucks up somehow because it's got this polar and it's got the non-polar. Somehow it works, I'm not sure they even know how it works, or how they came up with to use it as a breathalyzer, but they did somehow, So anyway, so they're trying to. So the goal here, and I think this is industry funded work, okay? So it's got Julia Higgins on it, she's a knighted in England, for basically for polymer work. So she's Lady Higgins. Where does it say that who paid for it here? Let's see. They changed where? Did you see acknowledgements anywhere down? Is it all? Oh, here. Right. So we thank that's where they did the work. That's just Beam Time and the Royal Academy of Engineering. Okay, so no one paid for it, I guess. Oh, where? Am I missing it? Oh yeah, but that's like that's mishmash. So nobody paid for it, I guess. It seems like it's kind of like consulting work in a sense, but Right, so that's what they make is like these nanoparticle. So the scale here, anyway, the size of them is given down here, right? So particle volume, particle size is somewhere here. Particle volume distribution.
So it shows what degree you fall.
Where? Oh, here, yeah. So it's nanometers, 16. So it's small. They're really small particles. How do they get that? They get it by this. So they take it. So the stuff is soluble in no, non-soluble in heptane and soluble in something else, DCM, some organic solvent. So it's soluble here. They take two jets, blast them, and they get a snowstorm of the particles. The phase separates when it gets to heptane. So this is the ternary phase diagram. Heptane's here, the polymer's there, and then the DCM is over here. So there's an immiscible. See the gray, which he calls red. They call that gray red in this paper. I don't know why, or brown. It's brown, right? So the green's miscible, the brown's immiscible. So it's a ternary. You find your mixture composition, and boom, you can get it to phase separate. So they want to understand this process by taking solutions of these things and looking at the chi parameter and then how the miscibility changes under different conditions, and then they also look at the particles. Anyway, they finally get the conclusion that they kind of roughly understand what's going on. I guess it isn't, the conclusion's weak, I guess, in this, but so they get a correlation between the concentration of polymer and the particle size, and that's what they end up. This is concentration of the PPPO. Yeah, and then the particle size changes with that. And then particle volume. So it goes with the volume, goes with the amount that's in it, you know, and then the radius goes with the cube root. I mean, the cube of the radius follows the concentration. And they end up with it's the same. Let's see, there's something about it's at the same, they figure out what the in the position of mixing, what's the concentration of the I think the concentration of some concentration there is the same for all of them. Like in other words, the particles have a certain solvent in them, and that solvent dries out and shrinks down to just the polymer, right? And the concentration where they freeze out or something is the same for all of them. That's like one of their conclusions. It's pretty complicated. I mean, it's too complicated to probably use, you know, but they are able to produce these, which I think must be done in industry. Like that must be how they do it. So this is called a solvent non-solvent phase separation, right? And this where it's called NIPS, and NIPS is used to make semi-permeable membranes. So there's a huge industry like Millipore. There's a bunch of companies that are making membranes, and the main way that they make the membranes is by this kind of process, like solvent non-solvent. And they get nanoscale pores, and you can use that for some kind of filtration, you know, for osmosis stuff, like an osmotic membrane. Right, so that's how they're all made, basically, this NIPS process, which no one really understands. So the ulterior motive is this membrane industry, which is lucrative. You know, so, I mean, you know, so basically, like if you're doing reverse osmosis in Saudi Arabia again, you know, and they have huge reverse osmosis plants, right? And then they go through those membranes like you know, water, so literally water. So yeah, so basically they're using a lot of them. So and the better you can make them, the cheaper you can make them, that kind of thing. So anyway, so they got that phase diagram, and they got to do 1, 2, 3, 4 like roots on this thing, you know. So I can get that better. Sometimes this is called a graphical abstract, but sometimes that's the best thing, you know. So they got this is just going on solvent quality too. And this is just going on concentration in the good solvent, right? One is the good solvent, increase in the concentration. So that's going to concentration blob. And this is going across reducing the solvent quality. So chi is getting more positive as you go across this way. And then they go into both. So this is concentrated and this is semi-dilute. So this is dilute, isolated chains. This is semi-dilute, where you see concentration blob. And this one's concentrated, where it's just all Gaussian across it, right? So they've kind of mapped out every possible combination of phase diagram in this thing. So they fit it two different ways. So the soluble one, they use that Ornstein-Zernicke function, the kind of bogus function. So the green is fit with the Ornstein-Zernicke function, and then the red, let's see, the green is fit with the RPA function. So they go, let's see, and the red is fit with the Ornstein-Zernicke function. When they get to the red, meaning brown here corresponds with the red there. Like somehow they weren't able to get red in this plot. I don't know why, but they call it red, but it's actually brown. All right, so anyway, so let's see. So they go through that business. They talk a little bit about NIPS, and they don't mention that it's the main use of NIPS is in membranes, so I don't think, which is a little odd. I tried to find a nice review paper on NIPS, and I found a 2020 PhD dissertation by someone at California Institute of Technology, which they did NIPS for membranes. So it's kind of odd. So that's definitely funded by some company like Millipore or someone, right? So because why would they do that otherwise? It's not like it's a pretty dirty operation. So you're not going to get a clean answer out of it. So it's not a model system or anything. Anyway, so so as you can see, even from this paper, that's exactly what they're trying to do, is get like science out of this industrial process, and it's difficult. It's not going to be that easy, especially if your viewpoint is not from the processing machine and then saying, how can I analyze that machine versus I have this whole toolkit of stuff that's designed to do something else, and I'm going to try to force fit it on that machine, which is what they did here. So all the stuff about polymer solution theory and stuff, that's like physics, right? That's got nothing to do with reality, really, not much. And then they're trying to apply it to this really applied topic. And they kind of, what you end up doing is in the end, it's just like whatever BS you come out with about, like you have your answers, your kind of analytic answers that are pretty clean. Then you have this dirty process and you say, well, they get larger and smaller because the concentration when they phase separate is the same or something, which is just conjecture. It's not really based on the results of the measurements. So okay, so there's a lot of, it's a nice paper, but there's a lot of ways you could rip it apart if you wanted to, put it that way. So anyway, they go through let's see, so they just say like the scattering. So this is from a guy named Benoit, who's a French guy from Henry Benoit. He wrote a book. Benoit and Higgins actually wrote a book together. So he came up with a function to say, like Debye came up with a scattering function for Gaussian polymer chain, but most polymer chains, when you put them in a solution, are going to be good solvents. So the Debye function isn't going to work for it, even though people will use the Debye function in a good solvent. So there's a lot of mistakes people make. I mean, because there's no other function, there's no other analytic function. So what you can do is you can take the, so Benoit in 1950, I think, or something, this is the way Debye calculated the Debye function. He just puts in this nu, which would be 1/2 for a Gaussian, but he puts in nu's like about 3/5 for a good solvent. And then you can do this integral, kind of analytically do that integral, and then you can get the scattering function from that as an integral. So Benoit is like 50 something. It's in French, that paper. So anyway, so and then this guy Hamuda kind of messed around with this. Hamuda was Benoit's postdoc. Hamuda's from Algeria. So the French, the French went into Algeria and made a mess there. Just like their Vietnam, more or less. And I think it was before Vietnam. You guys know about Algeria, right? Anyway, and they make this interesting mistake. When they colonize the place, everyone there is a citizen of France. Okay, so that means every Algerian. Any of you guys Algerian? Or anyway, we've had Algerians in here before. But anyway, yeah, it's North Africa.
Yes,
It's got a lot of people in it though. Like Africans move around, so there are southern or sub-Saharan Africans in Algeria. I mean, they aren't dealt with very well, but there are like this migration across the desert, right? So they're smuggling or whatever, human trafficking or whatever you want to call it. Anyway, everyone in Algeria is French citizens, like all the French, like Paris. If you go to Paris, like you go to a cafe, it's all Algerians that are serving you, you know, there's no French like in Paris. I mean, if you go to like Grenoble, the small towns are French, but a lot of the big cities are just Algerian. And the French are racist. That all Europeans are kind of racist at heart, right? So basically, especially the Italians now. But so anyway, so there's this conflict, you know, set up. They all speak French, you know, but basically this is kind of first class, second class citizen thing going on. And it's a huge legacy. Like at least we didn't make all the Vietnamese Americans, and we made some of them, but not all, you know. But anyway, it's a problem when you colonialize, you know. I mean, maybe it's just China has an advantage because they never really colonialized anywhere. So they're pure, you know, they're just like whatever they are, but like anyone else, like the British and everybody. So it's just a mixture. And then you get this problem that the people don't get along, you know, when they, anyway, so it happens. And that's what happened. So Hamuda came to the US anyway. He was in France, worked for Benoit, and then he came to the US and he worked at NIST, you know. He retired recently, but so anyway, he's I guess he would be an interesting character to talk to. I never talked to him about that kind of thing. Anyway, so anyway, he's retired. He's kind of gone now. So, so this is a function you can get for the ratio gyration for a good solvent if you want. And the ratio gyration is defined as our end-to-end distance by 6, like square root of end-to-end distance by 6 for if it's a Gaussian, and that's this function if it's not. And here's the friendly Ornstein-Zernicke equation, except you muff it up by just, right, Ornstein-Zernicke originally is wrong. And then you put in like M to be any number you want, so you can get any dimension you want, like 5/3 dimension. So M's 1 over the dimension. Or M's actually the fractal dimension. They don't call it that. They should just call it the fractal dimension. Then he stuffs in this other terms. This is a bogus function too. It's just like stuff in, stuff in. So this thing takes account that you have when you get to phase separation, then you get the large scale phases show up. So you see these things at low Q. There's a kick up at low Q because there's this micron sized domain showing up, and you just see the surface scattering from that. So it's a power 4 that cuts in at low Q. So they account for that power 4 by a fudge factor, the sum power n, which is 4. Like it's a surface of micron scale things. Then they just add in their good solvent thing, and they have some background thing. Right. So that's how they deal with when it phase separates. And when it's not phase separating, this is since they're using this function, they can't exactly do the RPA thing, because that would be RPA would be like let's see. That's this. So RPA would be like, this would be the Debye function for the chain. And this is what you get out when you mix it at higher concentration. So this is what diminishes it down. And this is the Debye function. But if you're not using the Debye function, you can't exactly do that. So you just say, well, I'm going to take it to 0Q. And then I'm going to get this chi parameter from the intercept here. The intercept's 1 over chi times the concentration. So you just can get the chi if you go to 0Q. It's there. That's an infinite size intercept of the thing. All right, so there's a lot in this. So that's what they do. They go to 0Q and they just get the chi from it. They just pull it out. And then they fit it with this thing. So this thing takes care of the low Q, and this is the high Q. They have 2 of these fractal scattering Ornstein-Zernicke like functions. With it, instead of 2 here, it's some random number. I mean, some power that's like the slope, the negative slope, or whatever they see. Anyway, that's not uncommon to do that. It's wrong, but it's not uncommon. So you can't really blame them much about it. But there's other ways to do it. That's the RPA if you have 2 polymers. So you have the 2 chi and then 1 over the intensities of the scattering. And then this is the resulting one. So if you have 2 polymers mixed, right, then it's this mesh of, we can go through exactly how you derive it, but basically, if you have this mixed mesh, they end up doing this inverse sum, right? Like a geometric average of the 2. So it's like the big one contributes less than the little one, right? So when you have 2 things mixed, the thing that has the highest intensity contributes less than the one that has the lowest intensity. So that ends up giving you this function that you measure, you know, and the way they mix is decided by this number, like what's the enthalpy of mixing. So that's what they do. They do that for their different systems through the three different. So this is their correlation length as it goes across concentration. So it drops because you can see smaller and smaller sizes as the concentration increases, right? And that slope, that's 75 is a 3/4 plotted again here, I guess. And then this RG is a large scale thing that they see, which is, they say it's 90 angstrom. There's a lot of problems with this thing. First off, if you look at their data, you can't see that 90 angstrom if you get what plot it's in. I mean, there's no, let's see, wherever the data is, it's like a kick up, right? So let me see if I can find that plot. So you need to see the Cuvier knee to get a size. Okay, so if you don't, like here. So this they're saying they fit with that other Ornstein-Zernike. So that's got kind of a Gaussian in it. Well, Gaussian is, see, you have these knees in a log. That's a Gaussian. That's RG, right? So RG like 2 pi over whatever that Q is there, right? So yeah, this knee here, that's their high Q Ornstein-Zernike. Their low Q Ornstein-Zernike is this thing, which is just a straight line. There's no knee. So you can't measure RG if you have no knee, right? You can't get it. So basically, this could be as large as it wants to be. Like this is another problem with that Ornstein-Zernike. It's giving you a size where there is no size. Like this line could keep going out to like a meter, literally, right? Or it could be at this point at 0.01, that's like your 90 angstrom thing, 100 angstrom. So it could be 0.01 microns, or it could be like a meter. You don't know because you don't see the knee part, so you can't tell how big it is. There's no possibility of getting how big it is, right? So that tells you when they plot this RG, that is absolutely completely bogus. There's no possibility of getting how big that is.
Function which is like converting this intensity to the size factor.
Not unless you know what the thing is that you're measuring, you know, like if you know the things, no, you can't do it. Okay. No, not if you just have a slope. There's no possibility of getting the size. You can't, the size is given by that knee. So you can't do it. There's not a way to do it. If you know exactly what the stuff is, you can get the surface to volume ratio from it.
Winner's function expansion.
You have to know exactly what the stuff is. And you can calculate the contrast. So you need other information. And then you could say, under the assumption that it's spheres, then I could say how big that sphere is from the Perot prefactor of it. And you get the volume to surface, which is called the Sauter mean diameter of it. So you can get a size, but basically the way they do it, you can't. It's not possible, you know. So that makes you think that some of this is just like they don't know what they're doing, even though the lady Higgins is the author on it, but she may be getting senile in her old age, you know. So who knows? She's nice. She's like one of the nicest people, right? So anyway, that's that RG here. That's what they're using that RG to do some stuff with. It's separate from this. They're two separate numbers, right? So, and then when they do this, that RG is a different RG than that. This is an RG for the theta condition of that size scale of the coils. You know, so this is okay what they did here. And they get the nice 3/4. So all right, so one thing they do is they say, we're in the good solvent, so exponents, this is 3/5 here, and then, or this is 5/3, 1.67, and then boom, it goes to 2. It's discrete transition, right? So if you, and we know like that isn't true, right? Like that's not how the things work. Let's see if I can get this. Sorry, I didn't get that plot up there. But, let's see if I can get this guy running. Oh, here. Bear with me. Let's see, do I have internet here? No, I don't have internet. That's all right, I don't need internet. I don't have internet. All right, this is important. Home physics, homework 6. Uh, homework 6. Digitize it. All right, so I think this is from figure 4 in the figure 4A. Yeah, there. So figure 4A, like this plot. Okay, so they have one thing that's weird is they have this background, incoherent background, and they talk about it over and over again, like the incoherent background, but they never like subtract it, which is weird. Okay, so and they should have subtracted it. So if you subtract it, then this is what you get. I mean, it's noisy. So that's weird. Huh? All right, so is that showing up? No, there. All right, so this is what you get. So the green is the original curve. Mouse is there. Huh? So the green is the original data, and it's got that background in it. They don't subtract, but you can clearly see like it's going flat. So you can just subtract that number, and then what you get is that you get a thermal blob. You get like the thermal blob thing. So you get -2 out here, the good solvent over here. So these are all the ones that are dilute. The dilute curves that they showed on the side. Let's see, the dilute ones are on the bottom row. They're changing solvent quality, right? And you should see across solvent quality is that transition from 2 to 5/3 shifting around. Anyway, the data shows pretty clearly like a thermal blob, like where at temperature, when it goes to 5/3, it eats more and more into it with the Gaussian. Or as you cool it down, the Gaussian expands up, right? So here they're going across concentration. That's like concentration of heptane 0, 11.9, 19.6, whatever. And then as the concentration of heptane gets higher, it becomes less miscible. Then it's phase separating out, and then the two parts should get bigger and bigger with that. And you can kind of see it if you do the subtraction of the thing. So that's taken their plot and digitizing it using this thing called Igor Thief, which is part of the Igor Pro thing. And you can just digitize the plot and then subtract off the thing and get the result from it. So anyway, that's that. I'll have a PDF of that, so you don't have to run Igor. But if you want to run Igor, I can kind of go through how that program works. I think it's pretty useful. Anyway, so that's that business. Let me just go through so they go across those lines and they get the different curves and they get the results from that. I think you can kind of see where they're going to. And then finally they say, so increasing the heptane, chi goes negative to positive, means it becomes immiscible. So they can measure the chi from the low IQ number. And then this is, as a polymer concentration goes up, they seem to show a shift in the chi, which they shouldn't see any shift. It should be just the same chi at different concentrations of polymer. It shouldn't affect it. So they see this behavior, who knows why. They say why. It goes on and on about why. It's almost like boring to read. I think I found the easiest way to read it is to start at the end, which talks about these particle sizes, and then go back and read it backwards. Because if you read it forwards, you fall asleep like pretty quickly. Like because they go on and on and on. But if you go to the end, like they get into their salient points or wherever they're really making stuff up, you can kind of, it's more interesting to read, I think, the last part than the beginning part. But anyway, they get particle size distributions from the micrographs. They change with the heptane concentration, with the polymer concentration. Those are going across the lines that they had. And then, so what's the questions here? So you have ternary phase diagram, dilute 1, 2, 3. There's 4 too, but it's been talked about 4. And then, so explain what happens to the structures as you go across those lines, right? In other words, draw the concentration blob pictures. So you have, where's their ternary thing? Let me just get back up here. This is a blow up of it here somewhere. All right, so there it is. So as you go across those lines, what's going on? So So here, this is going to be like a thermal blob happening, so you have the coil. So you're over here, good solvent and dilute, right? So that's just the expanded coil. And then as you worsen the solvent conditions, that's like lowering the temperature to go to UCST. So you're going to eat up, the small size will become Gaussian and it'll eat into the large size. So I'm not sure how you draw a cartoon of that. Basically, the small size is collapsing. So it's like you have your plastic, you heat it up and it melts and it pulls in, beads form. So that's what's happening when you go towards heptane there. Whereas solvent, finally, when you get to the brown, which is called red, you just have a clump, a Gaussian clump of the stuff, right? So it eats it up from inside out. Right, that's number two. Then number one, the concentration's increasing. That's the concentration blob. So you start dilute, expanded coil, you put the stuff in, the large scale becomes Gaussian and the small scale is still the same. Right, so large scale's collapsing, the small scale is still expanded until finally, when you get to totally, it's the opposite. Yeah. So how you draw a cartoon of that, I don't know. I would just resort to draw the scattering curve and say like that's how. Maybe take a picture at the 2 points. One's expanded, one's collapsed. Not try to put them together because it's difficult. That's why you can't do this with a TEM because you can't draw a picture of it. Like you can't do that. It's a statistical thing. Anyway, and then you go up in concentration, and then it's going to be 3 and 4 are going to be a mixture of these two things happening. So 3, you're at semi-dilute, and 4, you're at concentrated. So 4, you start out Gaussian, and then you go to pour a solvent, and then I think you're going to get kind of a coil collapse maybe, which starts also from the small scale up. Right, so you see in the coil collapse will be like the blob beads form, and then it. So I think 4 would be like a concentration blob. It's exactly the Grossberg model, like the picture of it. Then 3 is a mixture of 2 and 4. Like it's going to be complicated. You're going to have both a thermal blob and a concentration blob, and they're going to go at each other and have some kind of battle. Like who knows what. So 3 is going to be odd to look at. Anyway, so that's kind of so it looks like a bad question, but shouldn't be too hard to do. You know, maybe depending on your perspective, right? And then and that like these scaling theories is really important to get the cartoon because it is like kind of a cartoon. Like the whole thing is like a cartoon. So you have to, it's important to kind of draw the picture before you start thinking about it. Here 2b is log I by phi. So why does he do that? That's because intensity goes up with concentration. So you want to look at the ratio to get kind of a number that shouldn't change. And if it changes, it's changing because of chi. So why is I phi rather than I? Because if you just make it too complicated, if you don't remove the phi part, which is the simplest part. Once you remove the phi part, then the curves overlap each other. So you remove the complication of it. 2b. So here, they all lie on top of each other at high Q because you remove the concentration part. Otherwise, the curves would go up. Like here, these are no concentration, so they go up, up, up with concentration. But if you move that, they're all on top of each other, and they deviate from that at the concentration blob size. And the intercept over here is 1 over chi times the concentration. So at higher concentration, this thing goes up, I guess. I think that's how it works. Higher concentration should go down because it's screening more. So it goes down with higher concentration. Yeah, 1 over chi phi. So as phi goes up, this thing drops. That's right. So that's kind of what's going on there. And then you can measure the chi from that intercept, right? So you don't need any function to fit it. That's the absolute, because that's like looking at, that's the thermodynamic limit is large size. So you have small things moving around crazy, KT, and look at them at a very large size. They have a huge sample. That's the definition of thermodynamics. Go to 0Q, and then you get the thermodynamic limit. Infinite size, very small things. You know, so anyway, so there's that business. The data reaches a knee at low Q, it tails over some power. Why does this knee? What does this reflect? So that's the concentration blob. What kind of blob? It's a concentration blob, I guess. And then figure 3b shows the behavior of the blob size with concentration with power. So where is that? And that's in that slide set 3. Slide 3, page 13. Right. So it hasn't changed. So, and then 4A shows regime 2, dilute PPO as a function of reduced solvent quality. So that's going to be a thermal blob. Curves have a significant background. So that the solvent quality reductions like a temperature increase for UCST. So it's chi is 1/T. So it's kind of like if you're changing chi, you're changing kind of effectively changing temperatures as a thermal blob. And then it shows you this thermal blob thing in that digitized picture that you can open Igor. So I sent you the code for Igor. You can use it and you can open that experiment. It'll just show you that plot. Or I'm going to put a PDF of the plot on so you don't have too much problem with it. And then what power law do you expect? This is a 5/3 and 2 thing. What is a transition? So that's the thermal blob. And then comment on figure 3, or O'Connell proposes a discrete transition. So that's the problem. If there's a thermal blob, it isn't like a step function like he shows. It isn't like good and theta. There's no step. It's a gradual thing, and it's more complicated than what he's showing here. So anyway, that doesn't matter that much. Basically, you could critique it that way if you wanted. And then regime 4, so in S1 supplementos is partly, so regime 4, he's trying to get at this this process, like what let's see, this thing. So he's saying like all right, there, whatever concentration, then as it dries out, so it's all a dirty mess. You shoot the two together, the coils, you could have independent coil claps, but you actually have 100 chains in each bead that you have. That's what he says. And he shows a plot of how many chains per bead. And then they dry out and shrink down to these nanometer scale particles, right? So anyway, so that process, and then his regime 4 is kind of related to that process. In fact, all the regimes have to do with this process. So that question is just, how is this useful in the formation of nano PPPO for a breathalyzer? You know, I mean, in the end, like why did he wanted kind of the motivation for the work is to make a better breathalyzer. He didn't say that, but that would be like the motivation. Then like, does he achieve that? Like, how, can you do that by doing basic fundamental science on each of the steps, breaking it down into any possible sequence of routes that the thing could follow? Then what do you get from that? Like, is it really possible to like make an impact on something that way? I think the answer is no, but the people, all right, so if you do that, say you did that work and then you went to the breathalyzer company, they would love you, because they're every day they're turning cranks and running the extruder faster, or something's breaking and they have to fix it. And never do they stand back and say, how do I understand what is going on here? And that's exactly the person that every company needs. Like every big company needs a guy that can stand back and say, like, I understand exactly what's going on here, even if it's bogus, But if you can just say that, it gives them a glimmer of hope, like there is a light at the end of the tunnel, someday we will understand this process and we'll be able to like move on, So anyway, or improve something or make some kind of contribution to whatever. So it's surprising that it's always surprised me that you got a guy that knows how to run an extruder and the job is going to be run the extruder. Yet when they interview, they'll interview 100 people and they'll always pick out the guy that's trying to understand what makes the extruder turn or something, or like that's the guy they'll hire, always. And it's a pretty strange thing, like, that happens because actually the most useful guy is the guy that can turn the crank, because in the end, that's what the job is, But somehow they want to have this better kind of meaningful understanding. I think it must be something that comes from the upper administration. Like they see like there could be a way to solve their problems. But anyway, so hopefully this is okay. It's kind of it's a little bit difficult paper. And I'm wondering like, so the reason they're doing this, like Julia Higgins, this is a kind of bread and butter for her, this kind of study. So she's the last of the kind of the dinosaurs here. So I'm wondering like if this is the future, or you're really looking back at the past in this paper, even though it's 2022, but it's kind of like, you're not going to see a lot of papers doing phase behavior and RPA theory. This is stuff from the gens from the 1970s and 80s, So it's a little bit of a historic view. it might be useless. But you will see like Florey Huggins, everyone will say Florey Huggins. Like you'll see, if you do Florey Huggins Google, oh, by the way, that Chat GPT, I found out. So if you say to Chat GPT, give me references on like NMR of like polybutadiene in sulfur cross-linking. And it'll come back, it'll give you like 4 references. It won't give you 100, it'll give you 4, right? And then you look at those and they look like real references, but they, like you go to find that paper, right? The author doesn't exist, it's not a person. And the paper, it looks like a beautiful paper, almost exactly what you're looking for, you know? The title is made up. The machine's just creating things, like it can't give you the real references. It's a pretty big flaw. Like that tells you the flaw in that whole thing. Like it's not really, it doesn't really know anything at all, you know. It's pretty scary because you could do your whole dissertation using Chat GPT and have your whole like 500 references in there. If anyone bothers to check one of the references, and they look beautiful, they're perfect references, you know.
Titles are so like.
Yeah, and then who is this guy? So we go look, yeah, who is this guy? And it's like, oh, that name sounds kind of like Turkish or something, or maybe it's Russian or whatever. You can't exactly fix where the nationality is. We find out the name could be like Polish, you know, but then there's no one in Poland that does this work, anything like this, you know, with that, even that name or anybody at all, you know, so it's really weird. So there are flaws to that thing. It's beautiful how it works, but basically there's limitations that you should somehow be aware of, you know, like, so you can fool some people some of the time, but not everyone all the time. I guess is what the end of it is. But all right, so that's it for today. It went over a minute, but yeah.
Thank you.
All right. All right, feel the same. Chat GPT. It's like, I thought I had found the answer to everything. It's like, no. People are really riding on that artificial intelligence thing, you know, too.